Hello and welcome to an overview of NDT Care version 3.0 software. For more information, please contact us using the information provided on this slide in the lower left-hand corner. The capability of NDT Care version 3.0 software will be discussed here. First, we are able to display a loss of metallic cross-sectional area, also called LMA signal. Additionally, we can display localized flaw or LF signal. Further, we can display an interactive display of wire rope roughness or WRR data. This is a unique feature that allows the accurate quantitative assessment of the number of external and internal broken wires, single and in clusters, including inter-strand nicking, as well as the severity of corrosion pitting. Histograms, including automatic identification and marking of rope sections with inspector-specified deterioration levels, can also be displayed. We can identify and eliminate inspection artifacts caused by, among others, the so-called echo effect that adversely affects the accuracy of LMA signal calibrations for all sensor heads of the clamshell design. Movement of large steel objects in the immediate vicinity of the sensor head, spurious permanent rope magnetization, the end effect that occurs, for example, near wire rope terminations such as sockets, etc., varying load conditions, and finally stop, go, reverse operations. Further, we could look at signal calibration and level adjustment, and finally provide distance-aligned summary plots and histogram plots for reporting. In terms of a case study, we are going to investigate a 32 millimeter diameter locked coil rope. I refer you to the paper cited at the lower left-hand corner of the screen for more details about this case study and a comprehensive background on wire rope roughness. Given this construction, we looked at a rope that had been mounted on a mobile winch and was in service for approximately 10 years. Visual inspection of the rope showed corrosion in the first and second layer of the rope, as well as corrosion in the second and third layers. Let's now evaluate this rope test data using the NDT Care version 3.0 software. Opening a data file. To start the NDT Care software, we click on the icon provided on the desktop. Once the program finishes loading, you will see this user interface. There's a drop-down menu for which you can select the operation of choice. Notice we only allow certain operations at any given time. So right now you will see that I could open the file or exit the program. All other choice selections are grayed out, and even if I were to click on them, no action will occur. Finally, down here we have a log. There's a welcome screen, as you can see here. This is the 2019 version A of the software. So first I'll go by opening the file. A pop-up menu will appear asking for the file type. The software will allow us to use text file data formats, ASCII file formats, and CSV file formats. The ASCII and CSV file formats are legacy file formats for our older hardware. Any new hardware will result in the text file format. Notice that the text format is already pre-selected, so all you could do is click or just hit enter on your keyboard and that will be set. However, this is a legacy file format which happens to be ASCII, so in this case I will click the ASCII file format. A typical Windows pop-up will appear and you can see the 32 millimeter rope, which is the file I have here, shown as an ASCII file format. I will click that file and select open. Notice in the log menu that it shows the location of the file that was opened. Here I put it on the desktop, so it's just a good reference of where the file is kept and a log to show you what you have done. Displaying LMA and LF data. Once the file is open, we can go back to our drop-down, and we now see two different options available to us. First is insert time markers at 1 second intervals, and the next is displaying LMA-LF charts. You'll only need to insert time markers if the distance counter signal is missing or corrupt. So I will now go ahead and select Display LMA LF Charts, since the data provided in our data file has the appropriate distance counter signal. A pop-up menu appears asking for the number of meters per tab. So we want you to select an integer number of meters of data to display per page. The file opened is 26 meters long, and the overview plot will automatically appear on the first page. So what we're trying to do here is allow you a zooming function. So we'll create one plot, which will be the entire 26 meters long, and then there'll be various tabs on the plot where you can essentially zoom in. So I'm going to say I want to see 5 meters per tab. So I will generate additional plots showing the zoom at 5 meter intervals. So I'll select OK. Then a pop-up appears asking for the data direction. So how would you like to display the data, either in a forward or reverse direction? Notice forward is default, which you'll probably use for most of your applications. So you can either click it with the mouse or with the keyboard. I will enter just on the keyboard. Once the chart is displayed and the program is ready to go, you'll see the chart in the background and the graphical user interface pops up to the top with a log showing that the charts are displayed for the file that we opened. You can either minimize this or you can click at the figure in the back to access the figure and see what's going on. So I want to bring your attention to the upper plot, which is the LMA signal. Note that this axis is scaled and can be calibrated in terms of percentage loss of metallic cross-sectional area, or percent LMA. The lower plot is the LF signal. Note that the scale of this plot is arbitrary. The LF signal is a qualitative only and cannot be calibrated. Therefore, it cannot be used to determine or estimate the number of external and internal broken wires, single and in clusters, and the severity of corrosion pitting. As a consequence, it cannot be used to make rational rope retirement decisions. This has been amply demonstrated by impartial and independent round-robin testing. I can now click on the various tabs here to show a zoomed-in version of the overview plot. So again, the overview plot was the 26 meters, and then I can zoom in and you can see various features. So looking at the overview, I'll talk about this in a second. This is the calibration marker. Notice that it occurs around 10 meters. So I'm going to click on 9 to 14 where you'll see that 10 meter zoom. So really, it's a nice way to zoom in with way more accuracy than the overview. So I can go back and say this feature here occurs at roughly 5 meters, so I'll go 4 to 9 meters. And again, you can see that feature dipping to about -1% right here as well. And then finally in the 20 to 25 range, so I'll look at 19 to 24, we can see that it dips to almost 3%. Okay, here roughly -3%. So again, various zooms of the two LMA and LF signals. I want to bring your attention to a few of the things up top. First, I can directly print or save this if I want, or if I want to save this figure, I can click this, copy to clipboard, and then paste it into any Microsoft program, for example, Microsoft Word or PowerPoint. Additionally, I have this thing called Properties where I can change the axes. So perhaps I might want to change the Y and axes. So I click on that, and this pop-up menu appears, and I can basically pick the X and basically the Y-axis setting. So first for the LMA, notice it's -5 to 3, which is what we're showing here, the min and the max values. So maybe I want this to go to -4. So I can click there, go to my keyboard, type -4. Maybe I want 2 up here. And then for the LF signal, maybe a -1 and +2. So basically I can control the axis settings to what I want. So once I'm done, I will hit OK, and you'll see the zooms to the levels we picked, -4 to +2, and then -1 to +2 here for the LF. It does this automatically on all of the zoom tabs. So if I just pick a random tab here, you'll see that the axis change is complete on all of the zoomed tabs. LMA enhancement. We can now enhance the LMA data to reduce or eliminate various inspection artifacts caused by the inspection. To do this, the user will select the appropriate sensor head as part of the test equipment. From the drop-down menu, we'll select LMA enhancement, and a pop-up menu will appear for us to choose the sensor head. In this case, we used an LMA 250 to do that. So we'll select that sensor head. If you are unsure about the sensor head, please consult an NDT Technologies engineer and we can help you with that. For discussion of LMA signal enhancement, please refer to the reference paper previously cited. Notice a new chart appears, and for our log it says LMA enhancement performed for the file, and we'll keep a log of the sensor head here as well. I will now click on there, and again you can see in the title we refer to the sensor head used as well for future reference. I can go back and forth and compare it with the previous figure. Here's the figure, the original figure. Here it is enhanced. I'll go back and forth a few times. Notice around the 10-meter mark you can see the calibration wire. Get rid of the echo effects roughly here and here, and this becomes a little bit more of a square signal. Note that the calibration wire was attached to the rope and represents a roughly 1% increase of cross-sectional area. This is referred to as a moving calibration inspection. Notice just to the left or right of the calibration wires the area where the echo effect has been eliminated. Again, I will scroll back and forth. The original signal and the enhanced signal. I can then go back and change the axis scaling if I choose. And maybe for this plot I only want to go down to -3. All of the various zoomed tabs will take on that setting as well. LMA post calibrate. After the signal has been enhanced, we can perform a LMA post calibration. After selecting that from the drop-down menu, notice a set of crosshairs appear. We will take our calibration wire at roughly 10 meters. First select the lower part of it, and then the upper part roughly here. A pop-up will show you the percent difference between the two marks identified, and it says we're at roughly 0.65789% of that calibration wire. We might want to make that 1% or 2% or whatever you wish to desire. So you can put that in and select OK. Click on the figure that has been generated, and again notice we have performed a post calibration relative to the log. We can see here from 0 to 1, that's the area that we clicked, so that is now 1%. Notice in this area we are off scale, so we can go back to properties, change axes, and I will guess roughly -6. Looking at that, well, maybe -5 would be better, so I can go back. Again, just to show you that if you don't get it right the first time, no big deal. You just go back and keep changing it till you get the axis that you want. LMA level adjustment. The LMA level adjustment is performed now by selecting it from the drop-down menu. A new set of crosshairs appear. Notice that we're doing this on the LMA post-calibrated chart. So I will select where I wish the 0 to be, which I will pick roughly here. It shows how far that level is away from 0, and the desired value I want is 0, so this will shift that signal down. The log of that level adjustment has been recorded. I will click on that chart, and again you'll see roughly this 0 line is where I picked it. Alternatively, I could have picked it here, but this is where I wanted to show that chart. Notice I could also change the settings to roughly maybe a peak, leave it at -5, change that to 1, and I'll leave the LF signal. Click back, and again, as a reminder, it will appear, those axis settings will appear on all of the tabs. Displaying interactive WRR data. From the drop-down menu, we'll now select WRR. A pop-up menu appears titled Reference Scan Length in Units of Millimeters. The reference scan length is typically chosen to be equal to the rope lay length. The lay length is approximately 6.25 to 6.5 times the rope diameter. We know previously that the rope diameter was 32 millimeters. So I will multiply that by the lower end of 6.25. You can put that in a calculator. And you'll get roughly 200 millimeters. So I will enter 200 millimeters and hit enter to acknowledge that. Once the data is entered, a new figure appears showing the enhanced LMA, level adjusted and calibrated signal. The signal writing on top of that is referred to as our maximum BLMA signal, here shown in green. For more information on that signal, please refer to the paper cited previously. Next, down below is our WRR signal with a skyline plot writing above, which is essentially a reference envelope of the WRR signal. Note in the middle of the graph is a slider which refers to a scan length in units of millimeters. This is the same scan length width that we had entered previously in the pop-up menu. Note the 200 millimeters is what we entered. There's a slider that allows us to go to roughly 1/100th all the way to 5 times the scan length, and this is our interactive slider tool. You can use this tool in multiple ways. You can click on the middle point and drag it to a value, and everything will update. So in this case 510. Notice also the charts will display that value here, the scan length of 510, the scan length of 510. You can also go to various tabs. I'll click this tab. Notice this still appears. I could also enter a value. Maybe I want 300, and I'll hit enter. Notice the charts update to 300 millimeters on this axis and also in the title. You can also use the two ends, click, to get some adjustments as well. And in this case, we'll go by 10 millimeter increments. So any of those ways you can do it. I will go back to our 200 millimeters and make sure you can zoom in so you'll see on all the tabs the figures are updated. I'll go back to our overview plot. When you are completed and have the desired scan length, you can simply hit the Save WRR settings. As a side note, we chose the 1 to 5 lay lengths respectively to coincide with ISO code 4309. We've actually made our lay lengths even outside of that range slightly to provide the user with a little bit more flexibility. So a little inspection now of this rope. Looking at the LMA signal, notice that at roughly 3 and 5 meters, looking at the x-axis below, you'll see these dips in the signal. You'll also see them here and here and throughout the signal. This signal indicates winding on drum damage with a superimposed higher frequency signal, which is caused by corrosion pitting. At roughly 23 to 24 meters, you'll notice a dip in the LMA signal. This is referred to as corrosion-assisted LMA. Note that corrosion products do not show in the signal, but instead you do see a loss of metallic cross-sectional area. We can similarly change the axis settings here. I will leave the LMA, however I will change the WRR to roughly 2%. Again, we can utilize the zooming functions to look at these signals in a little bit more detail. Displaying summary plots. Next, from the drop-down menu, I will select Summary Plots. The summary plots basically just take the LMA as a %, LF, and WRR as a %, using the axis settings we have previously chosen, and just display all three of them on one convenient slide. You can see the overview as well as a variety of the zoom tabs. Displaying histograms with user-selected deterioration zones. From the drop-down menu, I'll select histogram. Crosshairs will appear on the summary plot that I just generated. I will select a region from roughly here to here of interest, so that will be the area of interest for me where I would like to perform the histogram. For this plot, notice we don't have the Properties tab, but instead we have a pop-up menu asking for any last-minute changes you want to make to the axes. You could enter them here, or if they look fine, you can just simply hit OK. We give you one last chance to accept them, or maybe you want to change them, and so you could hit redo. The menu will pop up again, and then you could make any adjustments. So I'll just hit OK and then accept. It'll first ask, do you wish to set a maximum deterioration zone for the LMA histogram? I will say yes. Instead of crosshairs appear, we can select that percentage. Here I picked 2% to define our personal deterioration zone. We can accept or redo that. I will accept this one. Notice it will highlight any region of the LMA signal that is below that roughly 2% that we selected. It then asks, do we wish to set a maximum deterioration zone for the LF histogram? I will say yes. So I can select, say, roughly 0.5. It will generate anything greater than 0.5 or less than minus 0.5. I could then say maybe that's not what I want, let me redo that, and instead of 0.5 I'll go right here, roughly 0.4. Now you could select either above or below, and it will always be symmetric. Also note that it only performs this histogram within the two vertical lines that I had selected. Clearly this signal is greater than 0.5, but notice it's not red, only the signal, and again here as well, that would be greater than 0.5 or less than minus 0.5. It will only look between these two vertical lines of the region of interest. I will accept that. It'll then ask for a deterioration zone for WRR. I will say yes. You could always say no and skip that, but I'm just going to show all of them, and I'll say maybe 1%. And again, I could redo it if I wanted to change it, but I will hit accept again. Notice, as previously stated, I have no means of changing the axis settings, so please make sure for the histogram you do it up front. So we now have the histogram shown for the LMA, LF, and WRR signals. The points selected here, the 0.51, that is this point right here, that's the starting point, and then the 25.5, that's the signal right here. So only between those two signals will we look at the histogram data here. I could then zoom in on a variety of sections, say, okay, there's this part, this winding on drum damage here at just above 5 meters, so I'll go to the 4 to 9 meter tab, and I'll see, yep, indeed, there's a little bit of that section right there. Okay. Also the LF, the WRR, will definitely see those sections of interest, so that might be a part of the rope of interest to you. Here was our calibration wire, as we would expect. And then maybe a little bit here, so around 19 to 24. We'll see just a couple little dips here, okay, on the WRR, LF, and LMA signal. So that might be something worth looking at. And then certainly right here, we have a lot of section of interest based on this loss of metallic cross-sectional area. So definitely an area we would like to inspect as well. And again, notice outside of this, we don't select anything because that's not the points for the histogram that were of interest to us. Saving figures. To save the plots, I'll just hit Save Figures from the drop-down menu. A new pop-up will appear. You can select the plots that you wish to save for reporting purposes. I'm just going to select all of them and hit OK. So it'll tell you we're now saving the LMA, LF figure. As it goes through, you can see up top, it'll go from tab to tab and save these first as JPEG images, and then we'll give you a choice if you wish to put it into Word. Now we are going to our Save LMA Enhanced figure. Again, you can see it going through the tabs. This will take a little bit of time. However, you will see that this automated process makes it much easier for reporting purposes. Upon completion, a pop-up will appear asking if I want to save these images to Word. I will select yes. It'll then import all those images to a Word document. You may not see Word appear. It'll do it in the background. When this is done, you'll see a folder appear called Saved Figures wherever you have selected the location. So since I did this on the desktop, that's where my file was, that's where that folder will be. So I can double click to open that. So you can see all of these JPEG pictures, and it will be, for example, LMA level adjusted, and you can see the 5-meter increments that we had selected. You'll also see the overview plot for each one as well. So you could use this to generate those, or again, you'll see if we scroll down a Word file called test results, I can double click that to open that, and you'll see the test results in Word. I can go to view, zoom, 200%, hit OK, and you will see the overview chart, first of the LMA LF charts. Then you can see the -1 to 4 meters, 4 to 9 meters zoom, etc. So you'll see this for the LMA LF charts. You'll see the various zooming going. The next one, and then finally this last one. Then the next thing we did was LMA enhancement. First the overview, then the various tabs. So I'll scroll through this. These are all the enhancements. And then we'll get to the next overview, which was our post-calibrated, and then the various tabs. So again, these will automatically insert these into Word. Level adjustment, WRR, and again, the documentation based on the scan length that we picked, in this case 200 millimeters. The summary plots will be next, etc. So you get the idea. All of the information is here, followed by the histograms, and then the deterioration zones that we selected. So again, for easy reporting, you can just do that.